Hi guys, in this video we'll be looking at redox in terms of electrons and then some examples of redox. We'll end the video with a summary.
A reaction, known as a redox reaction, occurs when electrons are transferred from one substance to another. For example, on the left-hand side of this diagram, we have a fluorine atom, showing its 9 electrons with 2 in the inner shell and 7 in the outer shell. On the right-hand side, we have a diagram that could be an atom of argon, but in this case represents a Cl- chloride ion, where the ion has an overall negative charge because it has one more electron than proton. If one electron is transferred from this chloride ion over to this fluorine atom, we would describe this as a redox reaction, leading to the formation of the F- fluoride ion and the chlorine atom. The name redox comes from the fact that reduction reactions involve two processes happening simultaneously. These are reduction and oxidation, giving us the combined name redox. We describe a process as reduction if it involves the gain of electrons. For example, if we have an Fe3+ iron cation, and this cation gains 3 electrons in order to form an iron atom, we would say that this is a reduction process, or that the Fe3+ has been reduced to Fe. On the other hand, if a substance gains electrons, we say it has undergone oxidation. For example, an atom of aluminium, which has an overall neutral charge, may lose 3 electrons in order to form an Al3+ cation. As chemical reactions always include plus signs to show addition and never negative signs to show subtraction, we draw our electrons on the product side of this reaction to show that we've produced the cation and the electrons from the atom. And we would describe this process as oxidation, and that Al has been oxidized in order to form Al3+. What we've written here for the reduction of Fe3+ to Fe and the oxidation of Al to Al3+ are known as half equations. This is because they show half of what happens in a chemical reaction. They show what happens to one reactant. Half equations can be added together in order to get an equation for an overall reaction. For example, here we can add together the equations representing the reduction of Fe3+ in order to form iron atoms and the oxidation of aluminium. Half equations are added together by first drawing one big reaction arrow. Then all of the species that appeared on the left-hand side of their reaction arrow within their half equation are written on the left-hand side of this total reaction arrow. So here we'll have Fe3+ plus 3 electrons from the first equation, which is the reduction equation, and then we'll have the aluminium atom from our second equation, which is our oxidation equation. We then do the same thing for the right-hand side of our big reaction arrow. From our oxidation equation, we have 3 electrons and the Al3+ cation. And from our reduction, we have iron as an atom. Our final step is to cancel anything that appears on both sides, as this hasn't changed moving from the reactants to the products. In this case, we can see that we don't need to write the electrons on either side, as they appear the same on the left-hand side and right-hand side of the reaction arrow. Once we've done this, we can write out an equation for the overall reaction, which is that the Fe3+ iron cation plus aluminium Al atom will react together in order to give Al3+, the aluminium cation, and iron. You can see that this is balanced, both for the substances on either side and also for charge. The total charge on the left-hand side is 3+, and the total charge on the right-hand side is 3+. We can still see that this overall reaction tells us that the iron cation is being reduced and the aluminium atom is being oxidized. This illustrates a general rule, which is that oxidation and reduction will happen simultaneously. And this is where we get the name redox reaction from. If one substance gains electrons, another substance must be losing electrons. So where we have reduction, we will also have oxidation. A useful way to remember which way round oxidation and reduction are is to use the memory aid oil rig. What this stands for is the oil part stands for oxidation is loss, and rig stands for reduction is gain. In both cases, talking about the loss or gain of electrons. A common example of a redox reaction in which reduction and oxidation take place simultaneously is what is known as a displacement reaction. A displacement reaction occurs when one substance which has formed a compound is kicked out by another. For example, if you bubble chlorine gas, which as always has the chemical formula Cl2, as halogens exist as diatomic molecules, through a solution of potassium bromide, you will form a solution of the potassium chloride salt and bromine molecules, which, as bromine is a liquid, will also be aqueous. They'll dissolve in solution. This reaction is an example of how a more reactive halogen can displace or kick out a less reactive halogen from an aqueous solution of its salt. As the reactivity of the halogens decreases as you travel down the group, chlorine is more reactive than bromine. Therefore, the bromine, which exists as bromide in the potassium bromide salt, will be replaced by chlorine in the form of chloride. As we'll see in a minute, this is also an example of a redox reaction. In order to write out equations for what's happening in this reaction, we need to remember that an ionic equation will only show the species that change during the reaction. For example, if this diagram represents our reaction, our blue circle represents our potassium, which is in the form of a K+ potassium cation, both in the reactant, potassium bromide, and also in the product, potassium chloride. This species is unaffected by the redox reaction. It exists as a K+ cation before and after the displacement. And as redox is a loss or gain of electrons, we can see that this potassium cation hasn't been reduced or oxidised, as it has the same number of electrons when the reaction starts as to when the reaction finishes. In redox, ionic equations will only show substances that have been oxidised or reduced, and therefore we wouldn't expect this K+ cation to appear in ionic equations for a redox reaction. For example, let's think about what's happening in the example that we introduced. We can start by writing out a reaction again in full. So on the left-hand side, reaction side of the arrow, we have Cl2 plus 2 lots of potassium bromide, or KBr, which we can write as 2K+, 2Br-, in order to give us 2 lots of KCl, or potassium chloride, which we can write as 2K+, 2Cl-, and our Br2 bromine molecule. From this, we can immediately see that we can cancel out our 2K+ from both sides of the equation, as we said, the potassium cation hasn't changed from the reactants to the products, and we therefore don't need to include it in our ionic equations. What we have left is our overall ionic equation for this reaction, which we can write as Cl2 plus 2Br- reacts to form 2Cl- and Br2. From here, we can then think about what is happening to each species separately. For example, if we think about chlorine, on the reactant side of the equation, we have a chlorine diatomic molecule, and this then goes to 2Cl-, 2 chloride anions. And how about bromine? On the reactant side, we have 2 Br- bromide anions, which go to give a Br2 bromine molecule. These are the beginning of our half equations for this reaction. And so far we can see that they're balanced for the number of molecules. We have 2 chlorines on the reactant side and 2 chlorines on the product side. However, what they're not balanced for is charge. And we need to add electrons in order to balance the charge and also to explain what is happening. For example, in order for a chlorine molecule, which has an overall neutral charge, to form 2 negatively charged chloride anions, this chlorine molecule must have gained 2 electrons, because these each have a 1 negative charge. Similarly, in order for 2 bromide anions to form a neutrally charged bromine molecule, each of these anions must have lost an electron, forming a bromine molecule and also 2 electrons. You can now see in both cases that the charge is balanced between the left-hand side and the right-hand side of the reaction arrows, and these are therefore our half equations. You can see if you added these half equations together, the electrons would cancel out from each side, and this is why no electrons appear in our overall equation. On the last slide, we introduced how we can describe a process in which a substance loses electrons as oxidation, and a process in which a substance gains electrons as reduction. If you look closely at these half equations, you can see that the half equation representing oxidation, or loss of electrons, is the second one, and we can describe this as 2 bromide anions are oxidised to form a bromine molecule. They each lose an electron, and if a substance loses an electron, we describe this as oxidation. But we described displacement reactions as redox reactions, meaning that reduction must also be happening simultaneously. And this is exactly what we can see if we look at the half equation for chlorine. Each of our chlorine atoms is gaining an electron in order to form a chloride anion. And we therefore say a chlorine molecule is reduced in order to form two chloride anions. Therefore, we've obtained half equations from our overall ionic equation, and these half equations allow us to see which substances have been oxidised and which have been reduced, and that both processes happen at the same time in this displacement reaction.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing GCSE chemistry resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make GCSE chemistry a walk in the park.